Here's another example of using the arc length formula. Remember that the length of a curve is given by t equals a to t equals b, square root x derivative squared, y derivative squared with respect to t. And in this problem, we're given our a and our b right here. So that's just going to be 0 to 2 pi up here and there. All right, well, what we need to figure out is what's my x derivative and what's my y derivative. So let's do that. So if my x is sine cubed of t, which I could write like so, then I'll bring down the 3, sine squared, derivative of sine is cosine. That's my dx dt right here. My dy dt, I need to start with what my y is. My y is cosine of t cubed. And so I'll get the exact same, except with sine replaced with cosine, and the derivative of cosine is negative sine. So we'll plug in our dx dt and our dy dt into this formula. So we're taking the integral from 0 to 2 pi of the square root. Dx dt is 3 sine squared cosine of t, all squared. And then for dy dt, we have a negative 3 cosine squared sine. And then let's, first of all, we should make sure we remember we cannot just cancel the square root with the squares. This plus here in the middle prevents that. So we can't make it that simple, unfortunately. We can distribute the square, though, and we should distribute the square everywhere here and here. So that gives me 2 pi from 0, square root 3 squared is 9, sine to the 4th t cosine squared, plus here we get 9 cosine to the 4th t sine squared dt. All right, so now so I cannot split up that square root. I really want to, but I can't because of this plus here in the middle. I can factor out. I got a square root, I got a 9, I've got sine squared here and here, I've got cosine squared here and here, and the leftovers, I took out all but a sine squared from the first, and I have a cosine squared left over in the second. And that's handy because that's a big fat square root of 1 is nothing when I multiply by it. So I'll just get rid of it all. And here I'll take the square root of the 9. There's no more plus in here. So the square root of 9 is 3. Now where I need to be careful is the fact that I need to take the square root of sine squared, and that's the absolute value of sine. Take the square root of cosine squared, that's the absolute value of cosine. And I can't just drop those those absolute values. The problem is that sometimes sine is positive, sometimes it's negative, and vice versa for cosine. The problem is that I don't, for values between 0 and 2 pi, they switch between positive and negative. And so I can't just get rid of them because sometimes they're actually negative, and the absolute value would change things. So I need a way around this. One option, the long way, I guess you could say, is to split this up into regions where you know sine and cosine are positive and negative. If you do that, then between 0 and 2 pi, they're both positive. From pi over 2 to pi, sine's still positive, but cosine is negative. All right, think of your unit circle here. From pi over 2 to pi, the x values are negative, so the cosine has to be, to make it positive, we have to multiply it by a negative. And then we just keep on going here. From pi to 3 pi over 2, they're both negative. And from 3 pi over 2 to 2 pi, the last leg of the journey, the cosine's positive, but the sine is negative. All right, this is definitely what I would call the hard way of doing this problem because you have to do 4 separate integrals. But let me point out a little trick here. Since in the original problem, x is sine cubed and y is cosine cubed, we're going to have, this is the case where x is cosine and y is sine. So it's the same thing except that in our problem, except that they are switched and cubed. So in fact, rather than doing it the long way here, I'm going to take advantage of the fact that the graph of this is going to be symmetrical. And in fact, the actual picture of this graph looks like an inverted circle. All right, the cube is what makes it squeeze in there because the fraction is less than 1. When you cube it, it makes it even smaller. And this is not the world's best picture here, but it is definitely symmetrical. So if you want to know what the length of the entire thing is from 0 all the way around to pi, you could just take a quarter of it from 0 to pi over 2. And so 1/4 of the length would be the integral from 0 to pi over 2 of 3 sine of t and absolute values, cosine of t and absolute values. And as we just noted that for between 0 and pi over 2, sine and cosine are both positive, so I can just drop those absolute values. All right, so now we're in business. Now I can just do a simple substitution. Let u equal sine of t. My du would be cosine of t dt. These are t values here and here though. So for t is pi over 2, that tells me that u is equal to sine of pi over 2, and that's 1. If t is equal to 0, my u is sine of 0, which is 0. So I'm getting u is 0 to 1, 3u cosine of t dt becomes du. All right, so that's 3/2 u squared from 0 to 1. So that's 3/2 minus 0 is 3/2. Almost there. This is 1/4 of the length, remember? So 1/4 of the length is 3/2. Multiply that 4 across. The length is 4 times 3/2. 2 times 3 is 6. And there's my final answer.